Last time we talked about Newton's first law, which talked about what an object did when the net force on it was zero. In this next segment, we're going to talk about what happens when there is a net force, or when the net force is non-zero. To get us started with that, let's watch a quick video and address what we see. Alright, so let's back it up a little bit and analyze this a little bit more slowly. Now what we have is a young lady who's apparently going parasailing and is not prepared for the boat to take off quite as quickly as it does. And so she's talking to our gentleman friend who's helping her out. And what we want to pay attention to here is right about here. She's standing there, innocent bystander, all excited. And remember Newton's first law. An object at rest will stay at rest unless acted upon by a net force. Now, if we consider where the net force is acting on this person, it's right here on her stomach. That's where the harness is. And so that means that that's where the initial force is going to be, and so there's no net force on either her head or her feet initially. And so pay attention to what her head and her feet do at first. Notice how at this point her head and her feet are still not moving. They're trying to stay where they're at. Their inertia is trying to keep them in the same position. The net force is being exerted on her stomach, which is moving away, but her head and her feet are trying to maintain their position. They're trying to maintain a zero velocity, or zero acceleration in this case, until the net force is exerted on them from the rest of their body. So, something to keep in mind. Now what you saw in that video also explains things like whiplash and when we're in accidents, when we're moving with our car and we stop very suddenly, we feel like we're getting thrown forward, or when you're in a plane that takes off very rapidly and you feel like you're getting pushed back into your seat. What's actually happening is your body is trying to maintain its motion. If you're on a runway in a plane, your body's trying to remain in that position, and so the plane is pushing into you to accelerate you. If you're in a car that's moving and you slam on the brakes, your body tries to continue to go forward even as the car is stopping. And so when you wear your seatbelt, now you're getting tied into the car more, and so there's more of the force being exerted on you. So today let's continue talking about dynamics, and today we're going to address Newton's second law, which again tells us what happens when there's a non-zero net force. And this law was first put down not in terms of the way that we commonly see it as mass times acceleration, but in terms of what we call momentum. So he said that the rate of change in momentum of an object is proportional to the applied force and the direction of the applied force. Now we more commonly know it as F equals ma. You may have remembered it from 8th grade physical science. But it's telling us what is happening to an object when there is a net force acting on it. And if we look at it in terms of the more common F equals ma, if there's a net force, then there must be acceleration. So let's look at it in the original form first, and we need to address this term momentum, though. Momentum is measured based on the mass and the velocity of an object. It's a measure of motion that takes into account both mass and velocity. And in this case, we're only going to worry about what we call translational momentum, and we talked about that term translational earlier. It simply means in a line or simply linear, and so you'll see linear momentum or translational momentum. Be comfortable with both. But the equation, it's just another 3-variable equation. P, which is momentum. This is our momentum. This is our mass. And this is our velocity. And so based on how we calculate momentum, we can see that the units for momentum are going to be kilograms times meters per second. And unlike with force, where our kilogram meters per second squared was the Newton, there's not a derived unit here for momentum. It's just kilogram meters per second. So, how did Newton first describe this second law? He said that the net force is equal to the time rate change in momentum. And notice that with our force and our momentum, we've got these nice little arrows on top. Those are going to indicate that they are vector quantities. You'll sometimes see them written in bold, and so when we're talking about vectors, you may see them written with arrows above them, or you may see them written in bold. Particularly IB likes to use the bold text. But how do we get to this F equals ma then? Well, if we take this equation, F equals delta P over delta T, and we expand it a little bit. And so what really is, let's thin this out a little bit, what is delta P? It's the change in momentum, right? And so if we say it's equal to the final momentum minus the initial momentum over delta T. And we saw earlier, we stated on the previous slide, that momentum is equal to mass times velocity. And so force then is going to be equal to the final mass times the final velocity, that's our final momentum, minus the initial mass times the initial velocity, that's our initial momentum, divided by the change in time. Now in most of our scenarios, the mass of the object is not going to stay the same. The mass remains constant. There are a number of scenarios where it doesn't. Mostly when we're talking about fuel being used. So if you're burning fuel, it's getting burned up, the exhaust is getting spit out, and so the mass is decreasing. But for most of our everyday situations, the mass stays the same. And so if we assume that the mass stays the same, that means that MF and MI are equal, and so they're the same value. We can factor it out. So we have M times VF minus VI over delta T. And hopefully we recognize this right here, VF minus VI over delta T. That's change in velocity over change in time, which is acceleration. And so from there we simply say, let's change the color here, that the force, the net force, is equal to the mass times the acceleration. And this is a derivation that you should know. Okay? And so that's where our current F equals ma comes from. Now along with momentum we have another related component, and that's impulse. An impulse is really just the change in momentum of an object. And so if we're looking at an object that is accelerating, or, well, yeah, accelerating, then its velocity is changing, its momentum is changing. If the mass is changing, its momentum is also changing, even if the velocity is staying constant. And the change in momentum, and if we do a little bit of, again, derivation, we know that force is equal to change in momentum over delta t. And so from there, the change in momentum is going to be equal to force times time. So F delta t, this is impulse, which is our J. And so force times time, if we're looking at a force time graph, the area under a force time graph is our momentum, because is the impulse rather. So this area right here under Ft, that is our impulse, that is our change in momentum. And momentum is one of our conserved quantities. Momentum cannot be gained or lost. It's simply transferred from one object to another. So within a given system, there's never going to be any loss of momentum. It's just going to transfer from one object to another. If we look at a system and it appears that momentum has been lost, there's something that's gone wrong. Either you've miscalculated, or you haven't taken into account the entire system. Okay, let's try and prove mathematically that momentum truly is conserved. We know from Newton's second law that the net force on an object is the change in momentum over a change in time, and this actually should be, because it's final minus initial, that should actually be a V here and a U here. Just notice that. So mv minus mu delta t. And the a's here are just to differentiate object A. So the net force on object A is equal to the change in momentum of object A over the change in time. Now, we assume that this change in momentum was caused by some force that was caused by, or that was exerted by, some other object B. We haven't gotten to Newton's third law yet, but the short form of it is that there are equal and opposite forces. And so if the net force on object A is delta P over delta T, there is an equal and opposite force on object B that is equal to negative F. And so all that is, the magnitude of the force is the same size, but it's in the opposite direction. And so the net force on object B, the negative F, is equal to the change in momentum of object B over delta T. And again, mv over mu, B minus mu. And so these two forces are going to be equal to each other, and so we can set them equal to each other. And what we find is that since the times are the same, the time over which is exerted is the same, the times can cancel out. And so we end up with, if we do a little rearranging, and I'll let you follow through this, but here's our momentum, our change in momentum of object A. Here's our change in momentum of object B. And if we do a little rearranging and we get all of the final momentums on one side and all of the initial momentums on the other side, we find that MAVA plus MBVB, so the final momentum of both A and B added together, is equal to MUA, MUB, the initial momentum of each one added together. So the total momentum before is equal to. So, number of things in this segment, but things to remember. Net force acting on an object always causes acceleration. That acceleration always occurs in the direction of the net force. This is Newton's second law. So we started with the net force is equal to change in momentum over change in time. We saw how that can be derived to give us F equals ma. Now here, remember, force and acceleration are both vectors. Those vectors occur in the same direction. So whatever direction the net force is, that's the direction of the acceleration. We also said that we have change in momentum, which is equal to impulse. That's force times time, net force or average force times time. And we said that the final momentum is equal to the initial momentum, and this is in a system, in a closed system. So, things to keep in mind as we move from here. The next segment will be on Newton's third law.